So when we analyze vapor pressure curves, it turns out there's a lot of information that you can extract from the curves. And so what we're going to do is looking at one aspect of the information you can extract. And if you take Chem 1B, there's a whole other aspect in this term that we call beta in the book, okay? The intercept of a graph. So this is actually a homework question. It's from the 5th edition. This is number 61. It says, this table displays the vapor pressure of ammonia at several different temperatures. Use the data to determine the heat of vaporization and normal boiling point of ammonia. So there's an equation called the Clausius Clapeyron equation. And it's actually a variation of an equation developed by somebody called Van 't Hoff. And so in this equation, what they determined was that if you take the log of the vapor pressure and then you graph it as a function of temperature. So think about how they would do the experiment. They would have a container and they would put a pressure probe in it, or a way of measuring the pressure, usually something like a manometer that we talked about in the gas laws chapter. And then they would change the temperature and look at the pressure change, and then change the temperature again, and then watch to see what happens to the pressure. Mind you, this is all done below the boiling point for the most part on these experiments. But this is the data that they would get. And you should be somewhat familiar, because we were looking at vapor pressure curves earlier, right? And they have this sort of exponential shape to them. So when you look at the data in this table, at 200 Kelvin, which is a relatively low temperature, ammonia has a vapor pressure of 65 torr. And then as you increase the temperature, you get increases in the vapor pressure. Now, there's a couple of ways that this equation can be used. One is to simply graph the data and determine the slope. And I'll show you how you do that in a second. But your x value will be this, 1 over t. So you would just take, for example, for one data point, you would just take 1 over 200 Kelvin like this, and that would be equal to 0.0005 per Kelvin is the unit. It's a funny unit, but that's what it would look like, something like that. No, sorry, that's, I'll change that. 0.005. There we go, like that. So that would look like something like that. Per Kelvin is still the unit, though. Now, to get this value, you have to use the natural log of the pressure. And so that's just, one of those functions on your calculator. And then you just graph that. And then you'd go ahead and you repeat that for this point, and then you would do that for this point. Now, that's the one way to do. Get a graph, and then the slope of the graph is b, right? It's something traditionally we call b for y. Oh, y is equal to mx plus b, so this should be m. I don't know why I put b there. That's equal to this. So if you multiply it by r, take the slope, multiply it by r, and then change the sign, that give you the heat of vaporization. There's another form of this same equation, and this is known as the 2-point version of the equation. I give slightly different views of these equations. They're the same equation that the book uses, but I prefer these formats. But it's the natural log of the pressure at one temperature divided by the pressure at another temperature is equal to negative delta H of vaporization divided by R again, so it's this part of the equation, times 1 over T2 and minus 1 over T1. So in order to do that, for example, if you wanted to use these 2 points, this would be your T1 or this could be your T2. It doesn't really matter which way you do it, as long as you make sure you use the correct pressure here, correct? And then you just plug the numbers in, and you can calculate for the heat of vaporization. I'm going to show you how to do both of these, because some of these math operations are probably not as familiar to you, and probably you need to review them a little bit. So here's the vapor pressure curve for ammonia. I thought I would graph it for you so you could see what it looks like. It starts with relatively low vapor pressure at low temperature, of course. And then as you increase the temperature, you'll notice for a 10-degree temperature change, the vapor pressure changes get to be bigger and bigger. And this is why we say small temperature changes can result in very large vapor pressure changes. The curvature of this line increases going upward like this. It's exponential. So at some point, it's going to be rising almost vertically with the temperature. All right. So how do we analyze this, right? So I'm just going to show you again how it's done, but this is with all the data and the graph. So this is essentially a completed analysis for the heat of vaporization. So what we did is we just took temperature, right, and said 1 over temperature, and we graphed that as the x value here. And then we said pressure in torr, and we just took the natural log of it. So for this point here is particularly this point here, right? That's the 4.179 for the y value and the 0.005 for the x value. Now as the temperature goes up, 1 over T gets smaller. So as a result, we're graphing these points in this direction when we do them. And this is the line we get. And then I just used Excel to generate the equation for the line. So I have M and that's going to be equal to negative 2969.9. The units are Kelvin. The units for natural log of P, essentially the units cancel out. And then you're left with the rise being unitless and the run being units of 1 over temperature. So these units come out in Kelvin over here. Because the rise over run, you're dividing by 1 over T. So in the units, it comes out as Kelvin. So R, the units for R that or the value for R that we use are the ones that have the units of joules in them. And so this is 8.314 joules per mole time Kelvin. And I know to use this value because I know delta H's need to be in joules. And this is going to solve out like negative delta H, right, is equal to negative 2969.9 Kelvin times R, which is 8.314 joules per mole time Kelvin. So the Kelvin units will cancel, the signs will cancel, and so I can just calculate delta H from that. So that comes out to be 24,000. Oh, you saw that there, right? I just did the calculation. 24,692. I have 3 significant figures, I believe, in these calculations at best. I think it's 3 because I think my temperature is all supposed to be with decimals on this side. So this is 3 sig figs here, so I'll take that as my significant figures. So this is in joules per mole, and then I'll move it over 1, 2, 3, so it's 10 to the third, right? So it's going to be 24.7 times 10 to the third joules per mole, which I can just write as 24.7 kilojoules per mole. So that's your heat of vaporization for ammonia. Now the question is, how do I figure out from this data what the normal boiling point is? And I'll work that out on the next slide because I knew I was going to run out here. But the reasoning is this. What pressure does the normal boiling point represent, right? What it represents here, 760 millimeters of mercury, or torr. That's the pressure for the normal boiling point, 1 atmosphere. So in essence, what we're doing now, I have this equation. I have the natural log of the pressure that I can calculate and plug into this equation and then solve it for the temperature at which the vapor pressure is 760. So let's work that out on the next slide. All right, so this slide looks a little bit busy, but let me walk you through it. We're looking for the the temperature when the pressure is 760 torr. Now this is the equation from the graph. So this is just this retyped without all the other stuff around it. And then this is the Clausius Clapeyron equation. And then I wanted to line these things up for you. What you're looking for is pressure. When the pressure is 6.633, the log of the pressure is this. So that's your Y value. And then your slope divided by R, that's this value here. This is your slope, right? So then we know that we're looking for that temperature. So there's your temperature. And this is just the intercept of the graph. And then what you're left with is solving for the temperature, or 1 over T. So typically, the easiest thing to do is to do something like this. 6.6333 minus 19.036, right? That's going to be equal to negative 2969 times 1 over T. And what I'll end up having to do is do the subtraction and then divide through by this number. Okay, so we'll go ahead and bring up the calculator. And I'm doing this because you got to be careful and pay attention to how you're doing the operations. Otherwise, you end up doing things you don't expect. So I'm going to go minus 19.036, then hit equals, and then divide by 2969. Change to sign, hit equals again. And then you end up with this funny little number that's down here, right? So that's what we have for 1 over T. So 1 over T is equal to positive, right? There's no negative sign on here. 0, 0. And then some people get in this trap. They'll stop the number here. But make sure you keep 3 or 4 digits. If you have 3 sig figs, you got to keep at least out to this point here. So we'll keep out to the 4 here. So we're going to go 0, 0, and then 41784. And we'll double check to make sure we got that correctly. 41784. Yeah. And this unit is 1 over Kelvin here. And you'll have to follow through the units that we use when we do these calculations, but really the only units are here. And so we'll end up inverting this number to get our temperature. So really just we're going to do this now. So that's 239.3 Kelvin. So T is 239.3 Kelvin. Now let's go back and see what the question really wants. Yeah, it doesn't say to do it in Celsius, so that would be the answer to the problem. So that is the temperature that the solution, or that the ammonia boils at when its vapor pressure is 760 torr. That defines its normal boiling point. Okay, so let's solve this same problem using the 2-point equation of the Clausius Clapeyron equation. And I'll show you, this is actually in some ways easier conceptually, but mathematically can be a little bit trickier. So we're just going to pick 2 points. So for example, we could pick this point and this point. And I generally like to pick points that are at the ends of the data because it spans the entire data set. So we're going to have to do natural log of P2 over P1. So we're going to go ln, and I'm going to call this 1 and this 2, okay? So make sure you keep track of your data real carefully. 235. Now, if this is not already, well, sorry, 235, 597. If this is not already in Kelvin, this is a thought that I was thinking, that you need to convert that for this calculation over here. So 597 divided by 65.3. So I'm going to go ahead and calculate that value because that's one of those things that people will stumble on, so we're going to go calculate 597 divided by 65.3, and then hit equals, and then we'll do the log of it. So the natural log is the one that looks like that. So 2.2129. Now, honestly, where people have the most trouble is with this calculation here. So we're going to go ahead and do that calculation separately too. So we're going to go 1 over T2 minus 1 over T1. And then I'm not going to, I'm just calculating the parts. I'll rearrange all this later and plug it all in, all these values in that we're calculating. But I'm just showing the bits and pieces of it right now. So we're going to do 1 over T2. So we got to look for T2. That's going to be 1 over 235, right? Minus 1 over 200. And then we'll calculate what that value equals. And this is actually where people have the biggest trouble on these calculations. They end up getting answers that are close but aren't quite right, or sometimes they even get answers that aren't even close. So the easiest way to do this is just say 1 divided by 235 minus 1 divided by 200, and then hit equals, and that's the number you'll get. So that's going to be 7.447, let's say, times 10 to the minus 4. The units are on this are 1 over Kelvin. You'll notice that this ratio of pressures in here, the units will cancel out. So this is why this ends up being unitless on these equations. Now, the last thing I have to do is I'm going to rearrange this equation. So it's going to be, the way it rearranges is going to be that, I'll do it in steps, I guess. Negative delta H over R is equal to the natural log of P2 over P1 divided by 1 over T2 minus 1 over T1. Now you can see why I calculated those bits separately. What I'm going to actually do is just stick these things in, and then I'll finish my rearrangement of my equation. So that's going to be 2.2129 divided by negative 7447 times 10 to the minus 4, 1 over Kelvin, like that. Now you notice that when this flips over, this will have units of Kelvin, just like we did in our earlier calculations. So I'm going to go 2.219 divided by, and I stored this earlier, this bottom result, so now we can just hit equals, and that's 2,979.8. And that'll be in units of Kelvin. So that's the value for negative delta H over R, and so now I'll multiply across by R. So now I'm going to be working with just these parts here. So delta H is going to be equal to R times, I got rid of this, I changed the signs here, right? So I got rid of those signs, times 2979.8 Kelvin. Again, R is 8.314 joules per mole times Kelvin. Rather than rewriting all that, I'll just plug it in and calculate it. So times 8.314. So 24, I got to change the sign, 24,077 basically kilojoules. So 24,774. But I'll go 1, 2, 3 like that. This is in joules per mole because the Kelvin will effectively cancel. So I get 24.8 kilojoules per mole. So let's see how that compares. So far, all this calculation right now is only for calculating the heat of vaporization. And when I did the calculation before, I got 24.7 kilojoules per mole, so a slightly different number. Now, you might be asking which one's better. Well, there's not a question of really which one's better. In terms of sig figs, these are essentially the same number. They're varying in the last place here. But in terms of which one's more reliable, it's probably the one that we got here. And the reason it's more reliable is it depends on more of the data. If you're just using 2 data points, the reliability is weaker because if one of the data points has an error in it, then all that error from that one data point, or roughly half of it really, gets distributed into your answer. But if you have an error in a data point here, then only about 1/5 of that error gets distributed within the rest of the data in terms of the calculation. So having more data points sort of helps to get rid of error that you have in any one data point. Okay, so this was all justifying the kilojoules per mole. Now what we need to do is calculate the normal boiling point of ammonia using this same equation. Well, this is kind of what we know at this point, right? We have the value for delta H and we have the equation. So now what we have to do is we have to solve for the temperature at which the normal boiling point occurs. And so again, just like we did before, we're going to drop in a 760 here, like this. And so what we're left with, and this is also kind of a tricky conversion, is solving for the temperature, right? And again, keep track of which one you're using as T1 and which ones you're leaving as T2. So we'll call that T1. Or actually, you know what I'll do is I'll use this one, the one that's closest to the data point, T1, and this will be 2. So what we'll do then is we'll substitute in. We'll need the natural log of P2 over P1, which would be 760 over 597. We'll solve for that, and then we'll do some rearranging to get 1 over T1 minus 1 over T2 minus 1 over T1 by itself. So I've done the rearrangement and done the calculations, and this is what you should end up with. And you notice I'm still keeping 4 significant figures in my calculations. So now what I'm left with is solving for T1. So I'll plug in 235 for T2. Right? So I'll rearrange it like this. 1 over T1 is equal to 8.101 times 10 to the minus 5th minus 1 over T2, and change the sign like that. Okay, that's to get rid of this negative sign. So I brought this to the other side, subtracted it from both sides, changed the sign. So now what I'm left with is plugging in for T2 235 Kelvin. So I'll go ahead and do that. So I went ahead and did the calculation. It comes out to be 4.174 times 10 to the minus 3rd. And then you take the inverse, and that's 239.6 degrees Kelvin. Probably only has 3 sig figs in it, really. So going back, let's see how that compares to our other answer. 239.3. So they're not that different, although, again, in terms of reliability, this calculation's probably a little bit more reliable than the other. So hopefully that helps you with that calculation. It is probably the most difficult calculation in the chapter, which is why I sort of separated it off as its sort of own video and gave you a couple of different ways to approach the problem.